Hello guys, and welcome to another calculus video. In this video of the integration guide, we are going to be going over the gamma function and also the beta function. So let's go ahead and jump right into it. So this is the definition of the gamma function right here. It's an incredibly useful function in integrals, and it pops up when you're solving a lot of different kinds of integrals. There are also some related functions such as the digamma and beta functions, which we will also be going over in this video. So let's go ahead and jump into it. So the purpose here is basically a lot of integrals can be transformed into forms of the gamma function. Sometimes this happens through the beta function, and very often the gamma function will be the only way to express certain integral results. So rather than having a closed form answer, we'll have to express certain answers in terms of the gamma function. Its derivatives also describe many integrals. So overall, integrators should understand how to use the gamma function, whether as a shortcut to solve an integral or as the only way to express a result. So here's the definition right here. The integral from 0 to infinity of t to the x minus 1 e to the negative t dt. So it is an integral defined function. This definition only applies for x greater than 0 because the integral diverges for x less than 0. Its most important identity right here is if we go ahead and take gamma of x plus 1, we get this integral right here. And if we apply integration by parts, integrating e to the negative t and then differentiating t to the x, we'll find that this term will just disappear, and then we'll get this integral right here, and notice that this is just gamma of x times x. So this tells us that gamma of x plus 1 equals x times gamma of x, which is an incredibly important recurrence relation for the gamma function, and it allows us to calculate a lot of values of the gamma function. So since f of 1 equals 1, gamma of 1 equals 1, that means that gamma of n plus 1 is actually going to be n factorial just because of this recurrence right here, which is exactly the same recurrence relation as the factorial function. Also, using this relation right here, we can calculate gamma of x for x is less than 0. So for example, right here we have gamma of 1/2 equals square root pi, and this can be shown from the Gaussian integral. If we wanted to calculate gamma of negative 1/2, we can't use the integral definition because, again, that integral diverges, but we can go ahead and plug in this formula here. If we let x equal negative 1/2, we find that gamma of 1/2, which is square root pi, equals negative 1/2 times gamma of negative 1/2, which would allow us to calculate gamma of negative 1/2. And another important identity is the reflection identity right here. I won't have a proof here, but essentially it is a infinite product based proof, and essentially gamma of x times gamma of 1 minus x equals pi cosecant of pi x. And this is very, very useful, so definitely keep this in mind. Sometimes you may have to use both of these identities together to express a result. So in general, gamma of n and gamma of n over 2 are easily expressible. So obviously, gamma of n is going to be some form of factorial, and gamma of n over 2, you can extrapolate from gamma 1/2 equals square root pi, and then just sort of use this identity to find the value of gamma of 3/2, gamma of 5/2, etc. But unfortunately, no other value of gamma of p over q is known or expressible in terms of normal functions. So we'll just write, for example, gamma of 1/3 if that's the answer for your integral. There's no other way to simplify it. And so that's how you'll write those types of answers. So let's look at one class of integral, which is where we're able to apply the gamma function directly. So some integrals, we can just directly convert them into the gamma function, and that's how we're going to be able to actually evaluate them. So, for example, this very nice generalized integral, which is honestly a result that everyone should know, the integral from 0 to 1 of x to the a times ln x to the b dx. We're going to make the substitution x equals e to the negative t, and you'll see why we do this in a moment. After calculating our differential and plugging in, we get this expression right here, and once we simplify, we get negative 1 to the b times the integral from 0 to infinity of e to the negative a plus 1 t times t to the b dt. Then we let a plus 1 t equal v, then dv over a plus 1 equals dt, and then we go ahead and simplify everything again, and right here, our job is to notice that the integral from 0 to infinity of e to the negative v times v to the b dv is gamma of b plus 1, which gives our final answer as negative 1 to the b, gamma of b plus 1 over a plus 1 to the b plus 1. So in this case, if b is an integer, then this will become a factorial, and otherwise, this will just be expressible in terms of the gamma function. So a lot of integrals like this, especially if we're looking at something from 0 to 1 and we have natural log of x, it might be worth it to try and convert it into an integral from 0 to infinity using this substitution right here, because we might get some form of the gamma function. So in integrals from 0 to infinity, look for combinations of e to the x and x to the p, because you can likely apply the gamma function. Try expanding functions as power series. This one's super important, making substitutions or using Feynman's trick to convert other integrals into this form. And then what we just discussed, if you're going from 0 to 1 and you see natural logarithms and power functions, you can sometimes also use the gamma function there. So actually, some of the practice problems that I have right at the end, they will involve using power series and combining them to sort of turn something that isn't of the form of e to the x and x to the p into something that is the form of e to the x and x to the p. So another interesting property of the gamma function is that it takes part in a very interesting function called the beta function. Not to be confused with the Dirichlet beta function, is an interesting intermediary between integrals and the gamma function. It has three really important identities, and they're all shown below. Obviously, here's the base definition here. Well, actually, I think this is the formal definition, but this is the most useful expression. Beta of a and b is gamma of a times gamma of b over gamma a plus b. And then it also has these integral representations. The main way that we're going to use the beta function is we're going to find one of these representations, and then we're just going to go ahead and plug in the beta function. And sometimes we'll have to do a little bit of legwork to get something into this form. So that's our first example problem right here. This is my favorite integral formula. The integral from 0 to infinity of x to the s minus 1 over x to the n plus 1. And so this is one of the cases where the beta function can absolutely destroy this integral and make the proof really, really, really easy. So if we let x equal v to the 1 over n, we're going to get this expression right here. And then we just have to rewrite it in the form of this expression for the beta function. So it's really useful to sort of remember all three of these. Again, obviously memorizing formulas isn't the best thing. I do have a video that proves all three different forms of the beta function. If you guys want to go ahead and check that out, I'll link it as a card. So maybe that'll help you to actually remember the formulas, but in general, having these on hand, especially if you're going to an integration bee or something, is definitely going to help you a lot. So anyway, we can sort of get it into this form of the beta function, as you can see right here, and we end up getting 1 over n times gamma of s over n times gamma 1 minus s over n all over gamma 1. Now gamma of 1 is just 1, and this right here is the perfect time to apply the reflection formula, giving us our final answer of pi over n times cosecant pi s over n. Now, finally, the most important trick right here with the gamma function is combining the gamma function with partial differentiation and the digamma function. Now, I have a few examples and an explanation here, but if you want more explanations, I do have another example using the gamma and beta functions in my video on the Feynman's trick, so I'll go ahead and link that as a card as well if you want to check that out. So we can actually differentiate the gamma function and find an integral representation for the derivative of the gamma function, and this actually gives us the answers to a lot more integrals. So for example, if we differentiate gamma of x, we just have to bring this differential inside the integral, and we end up with the integral from 0 to infinity of e to the negative t times t to the x minus 1 times the natural log of t. So the only thing that changed is we got this extra natural log. And if we differentiate again, we get natural log squared, and so on and so forth, as you might imagine. So let's look at an example right here. Here, notice we have this natural log squared, which means we'll be looking at the second derivative of the gamma function. And in this case, we don't have any t to the x minus 1, so that means that our x is 1. So this means that this integral right here is equal to gamma double prime of 1. But how do we actually calculate gamma double prime of 1? There's no way to directly calculate gamma double prime of 1 unless you want to try and evaluate this integral by another method, but there is another auxiliary function that can help us out. So the digamma function is very interesting. It's the derivative of the natural logarithm of the gamma function, and it's equal to gamma prime of x over gamma of x. Now, I have separate videos on calculating values of the digamma function and also of the polygamma functions. So I'll go ahead and link those if you guys want to check them out. And essentially what we do to find gamma double prime of 1 is we take the gamma function, the digamma function, sorry, and then we differentiate it. And when we differentiate it, we just use the product rule, and we get this expression right here. And notice what we really want to solve for is gamma double prime of x, which is right here. So all we have to do is plug in x equals 1, and then we can evaluate digamma of x and trigamma of x using tricks that I mentioned earlier that are shown in those videos uh, that I've linked to this video. So then all we have to do is actually solve for gamma double prime of 1, which just happens through reorganization right here. And we have the integral from 0 to infinity of e to the negative x times natural log of x squared dx. And this is equal to gamma double prime of 1, or pi squared over 6 plus gamma squared. Here's another example right here, where instead of using the definition of the gamma function, we're actually using one of the expressions of the beta function. So notice if we have this expression of the beta function, x to the a minus 1, 1 minus x to the b minus 1, and we take the partial derivative with respect to a, this gives us this very nasty quotient rule over here. And but the net effect right here is that we actually get x to the a minus 1 times natural log of x, again from that partial differentiation. And this allows us to evaluate this integral over here. And once we go ahead and plug in our values, a equals 1 and b equals negative 1/3, we get our final answer right here. This can be simplified, I believe, to in terms of rational functions, but I'm not going to go ahead and bother doing that because it seems like a lot of work, or in terms of normal functions, but I'm not going to go ahead and do that because I made this video essentially at 11 p.m. and I'm too lazy to do that right now. But if you guys want to go ahead and try to evaluate this using the tricks that I mentioned earlier, be my guest. And finally, remember that the gamma function usually only shows up after using a different strategy. If you're in an integration bee or you're looking up integrals online, they're not going to give you an integral that's already in the form of the gamma function. You're going to need to work for it, and you're going to need to notice when it's time to actually apply the gamma function. So this usually happens after expanding something as a power series, where each term becomes an expression of the gamma function, which can be converted into a factorial. Or often it'll happen after a series of substitutions. Again, you can see my video on Feynman trick for more ways to combine the gamma function with other methods. Finally, let's go ahead and look at some practice problems. A few things to note here. First of all, for this one, you need to use the zeta function. And for this problem here, there will not be a closed form, so it's going to still be in the form of a summation. It's just a very cool looking summation. So this is actually called the sophomore's dream integral. I believe I do have some more practice problems down here if you guys were not able to figure some of these problems out, feel free to join my Discord, and I'm happy to walk you through them or give you the answer if necessary. And yeah, so these are some very tough problems, so, give them a shot if you want, but if you can't figure them out, don't worry. Thanks for watching. I hope you guys enjoyed the video. Thanks, and I'll see you next time.